So, a couple of weeks ago, the IEEE posted the results of a best language survey, and Python did pretty darn well, I thought. You can see that they even categorized the languages by where they're usable. Apparently, they hadn't heard of MicroPython. It's the creation of Damien George, who's the recipient of the PSF's Genuinely Nice Chap Award for his service to Python and the Python community at large. Damien actually has a background in theoretical physics, robotics, and computer engineering. He loves to program and build things. And he's actually made a successful company out of the MicroPython project and the Pi board. And he's brought it to makers, I have a couple, and teachers and industry developers around the world. And he's worked with the BBC on their amazing microbit project as well. And there's even a space angle with the European Space Agency taking MicroPython into space. So I'd like to welcome Damien to the stage to talk about his journey from Kickstarter to space with MicroPython.
Thanks, Richard. Thanks a lot. So my slides should appear. But so you've all heard that there is a code of conduct for this conference. And basically it means to be awesome to each other, which I think is really awesome. But it also means you need to be awesome to the speaker, and you need to laugh at all their jokes. But that wasn't a joke, right? But you're not allowed to laugh when it's not a joke. And the speaker's not allowed to confuse the audience either as to when they should laugh or not. So that's confusing. Anyway, so, okay, if my slides appear, I can start talking.
Hold on a sec.
But I can start talking without them. So I'll just give you a little bit of background about myself so you understand where I'm coming from. I did a PhD at Melbourne Uni here, and then that was in theoretical particle physics, high energy physics, like extra dimensions and cosmology and so on. And then I moved to Amsterdam and did a postdoc there at the Dutch Research for Atomic Physics. And actually, right next door to where I was working was where Guido invented Python many, many, many years ago. So that was really, really interesting. And then after Amsterdam, I moved to Cambridge, University of Cambridge, and a postdoc there as well in theoretical physics, working on supersymmetry and inflation and Higgs boson physics and so on. But during my time in Cambridge, so I also did a computer engineering degree at Melbourne University, and I always kept up an active interest in programming and robotics and building CNC machines and all these other things. And when I was at Cambridge, I thought, it might be fun to do a Kickstarter, just for the sake of it. Everyone else was doing it. And so I thought, well, I'd always wanted to try running Python on a microcontroller. So I'll see if this can be fit into the Kickstarter format. So I thought I could make a little board to give people as a reward. And yeah, that turned out to be really successful and took over my life. And then I transitioned slowly from physics to MicroPython. I mean, I don't even know what I am anymore. I guess I'm just a scientist who does stuff. But and eventually, yeah, built a company around MicroPython, and I'll talk a bit more about all those things in the talk. Okay. Let's see how this goes. So what was the motivation for making MicroPython? Well, these days, microcontrollers, which are really small computers, like that one there on in the picture, they have a lot of functionality in such a tiny package, like a CPU, and then all these peripherals to do things like convert voltages and timers and interrupts. And in order to control that, you need to code it up. And traditionally, it was done in assembler or C. But as you know, programming in languages like assembler and C is difficult and time-consuming. So I thought maybe it would be a good idea instead to be able to use a high-level language to program these more sophisticated devices. And I chose Python to try and do that. And the main thing for me, because coming from a physics background and a research background, it was more of a research project for me as well. It was like, can this even be done? Python's such a large language. Can it even run on a microcontroller at all? So I was approaching it from the point of view of research and enjoying it from that point of view, not from like a software engineering point of view or this is what I think the world needs. It was just something intellectually stimulating for me. And why was it so difficult? And it's because Python uses a lot of memory, basically, lots of RAM and ROM. So ROM is read-only memory, like your hard drive, sort of. You can think of it like that. And on a microcontroller, you only have about, say, 0.5 megabyte of ROM to put all of your stuff, your files and your code. And the RAM is around 64 kilobytes. So it's really, really tiny. So you need to run everything in such a small environment. Why did I choose Python? Why didn't I choose JavaScript or Lua or Ruby or some other scripting language? Well, at the time, I didn't actually know Python very well. I'd used it a little bit, but I thought, oh, this would be a good chance to learn Python as well. And I thought, how hard can Python be? It's like if, for, it's pretty basic. And then, the more and more I got into it, the more I realized how such a sophisticated language it was with all these features, and took quite a lot of time to implement them all. But anyway, I was very naive, and it was good that I was naive. It's always good to approach things from a very naive point of view. Otherwise, you don't do anything at all. And Python has a really good community, as we can see here, really large, great community, lots of people friendly on the internet, willing to teach you how to use it, lots of tutorials, lots of debuggers and developers and libraries and infrastructure that already exists. So by choosing Python, I was leveraging off that instead of implementing my own language, for example, or a different one. So that was one of the big choices for using Python. I also think Python is really, really easy to learn. If you're here and you're new to Python and you've never tried it before, it's a really easy language to start with. You can do something simple very quickly. But then as an advanced user, you don't run out of steam along the way. So you keep learning and learning and learning and learning. And you keep learning. And even today, I still learn about stuff, even though I've implemented Python, basically. So, the learning curve is shallow, but really long. And I think it's great for both beginners and advanced users, because it keeps people interested in the language. And it also evolves all the time. It has really good operations for microcontrollers, because when you're working with bits, you want to be able to do AND and OR and XOR, and Python provides these features for you. And it has a good distinction between integers and floating point numbers, which is very important. And because Python's compiled, you can actually do some optimizations. In fact, there's a lot of work at the moment developed on the Python dev mailing list about optimizing CPython to make it faster and faster, advanced compilation of the bytecode. So that's really cool. So why can't we just take normal Python? So CPython is the normal Python you use every day, mostly, on your computer. Why can't we just take CPython and compile it with space optimization, as in minus OS in GCC, so that it fits on a microcontroller? And the reason is because internally CPython doesn't really care about memory usage so much. So it uses it liberally. It doesn't use it excessively, but when you're talking about 64 kilobytes of RAM is all you have, then things like integers in CPython, each integer, like the number 1, takes about 16 bytes of memory, because you need to point it to its type, being an integer, its reference count, and then the number of limbs and the limb value, which just for number 1 is about 16 bytes. And so CPython, in order to be more efficient, it pre-allocates all the integers from -5 to 255. And that uses about 4 kilobytes of memory when you just start Python. And that's already eating into a significant amount of memory on your microcontroller. So this is not a very good thing. And it also means every time you want to do some addition, like 100 plus 200, I've got to allocate memory for the result for 300. So in CPython, it's not slow because memory is abundant, but on a microcontroller, this is a problem. The other thing which requires memory is if you do a method call, you have to LED.on, for example, you've got to extract the on method from the LED object, and you make a bound method object, which takes our memory, and then you call this bound method object. And this takes up a little bit of memory. But if you're going to do this thing hundreds of thousands of times in a loop, you're going to be eating through lots of memory, running the garbage collector, so it's going to be a bit slow. And so the idea with MicroPython was to rewrite Python from scratch. So I didn't take CPython and just change it. I just started from zero and implemented Python in a new way so that it was optimized from the beginning not to use memory where possible. So the main thing is don't use memory. So for those who haven't seen MicroPython in action before, I'll do a quick demo just about what it is so you can understand, so you have a bit more in mind what's going on here. So you don't need to see anything, but it's just this is our Pi board, which runs MicroPython. But most of the stuff you'll see will be on the screen here. So okay, so I log in here. Now, I just have to explain what's happening. So the computer is not doing anything special. It's just sending characters down this wire, this USB cable, to the chip. The chip decides what to do, and then it sends characters back. So it's just the computer's acting as a very dumb terminal. So if I press the letter A, it just sends A down the wire, and then this microcontroller has to decide what to do with that A. And because it knows I'm at the prompt, it's like, okay, he's typing an A, give an A back, and so it looks like he's typing an A. But anyway, the microcontroller has to do all these things. So this is the end of the talk. That's it. Thank you. But you can, 1 plus 2 is 3. But the point is, okay, you can see that's a 3. That when I do 1 plus 2, so it sends the 1, it sends the plus, it sends the 2, it sends the enter. And then the microcontroller is like, well, what do I do with 1 plus 2 enter? And it knows, okay, I've got to compile that into bytecode, and then I've got to execute it, and then I've got to print the result out. And all of that is done on the microcontroller. So it looks at this string 1 plus 2, it turns it into tokens, and it compiles it, and it prints the result out. So the compilation is all done on the microcontroller. It could be running with a battery sitting in the corner over there doing all this stuff on its own. It doesn't need to be connected to the computer. So this is just to set your expectations of what's happening here. But this here is a full, as full as we can make it, Python sort of interactive prompt. And you have things, you have floating point numbers and math module, so sine of a half, around about half. And then you have, say, big numbers, so 1, 2, 3, 4 times 4, 5, 6. Well, that's not very big. But if I do, let's try 1, 2, 3 to the power of 4, 5, 6, that's a bigger number. So, but it has all the features of Python. You don't, it's supposed to be, Python on your computer, Python on the microcontroller. It's the same thing. And it has, so we can have a look at, so there's a MicroPython module, and we can have a look at the memory that's being used. So it says GC total 102,400. So this microcontroller has that many bytes of heap, 102 kilobytes, 102,000 bytes of heap, and it's used 1,300 of them to do what I've already done. And then this diagram down the bottom showing you which parts of the heap is used. So you can see it doesn't need much memory just to do what I've been doing, import math module. If I reboot, that was and try again. It's also got tab completion. That's why I can type so quickly. I'm only using 480 bytes of heap just from a fresh start. So the other things, it has a built-in file system. So import os.lister. So these are some files in the file system. I'm actually in, if I put an SD card in, I'll have another sort of directory mounted on the SD card. But I can use f equals open to read my boot.py, which is run on boot up. So it's really trying to be Python as much as it can. And you can store your Python code on the internal file system and import your code that you wrote and do all these fancy things. Okay, so this is just to show you what's possible. There's so many things I can do. Maybe I can show you just quickly the accelerometer demo. So if I make an accelerometer object, so AC is now my accelerometer, which is built into the board. And I think it has an X method. So let's make a loop while true, print the X value, and then let's just wait a little bit so it doesn't print so much stuff out. Okay, so this is the X angle of the board. So if I adjust the angle of the board, 0 is when it's flat, and then it goes from minus 20 to plus 20. Well, I think it's minus 32 to plus 32 is what it's supposed to go between. But if I shake it, you can. Okay, but then you just press Control-C to break out of the loop, and you can keep doing stuff. So there's lots of hardware. You can play with lights and an accelerometer, and you can attach things to it. And you have an I2C bus and a UART and an SPI and SD card, a CAN bus, ADCs, DACs, timers, interrupts. You can do hardware interrupts. Lots of cool stuff. So, okay, that's just sort of an introduction to MicroPython and how it works. So you can know what's going on. Let's continue with the talk. So the title of the talk was From Kickstarter to Space. So I explained already how the Kickstarter came about. It's because I thought, let's see if people like this idea. Kickstarter is a good way to sort of bootstrap your idea. Are people interested in what you're doing? At least that's what it used to be. Because this was done almost 3 years ago now. And today Kickstarter has turned into a bit more of a, well, we already have a product, it's almost ready, we're just going to use Kickstarter for advertising. It's a bit of a shame. But anyway, so I wrote the first line of MicroPython in the 30th of April 2013, over 3 years ago. And I remember writing the date down because I'm like, it's nice to have a history of when you started something. And then in September of that year, there was a flashing light and a button running on the microcontroller. And then a month later, I was able to attach USB and have a file system. And at that point, I'm like, okay, this is minimum viable product. This is ready to show people and ask if they're interested, and then I can continue developing it further. So with my lovely wife, we made a video, which is, all Kickstarters need a good video. But I think it's good to be honest in your video. Just have you standing in front of the camera and you just talk about your stuff. And it's the best way to make a video, and that's what we did. And the next, then you go through the process with Kickstarter. We launched it in November of 2013, and we got a really great response, many more backers than we thought we would, almost 2,000 backers, and raised nearly 180,000 Australian dollars when converted from pounds. And then I officially called it finished in April 2015, which was only a year ago, because it took so long to do all the things that I promised I would do. If you do a Kickstarter, don't overpromise. That's the worst thing. And just note that Kickstarter itself as a company has raised over $1 billion in funds for its projects, which is a massive amount of money. Kickstarter is a phenomenon these days. I mean, and yeah. It's a pretty crazy ride doing a Kickstarter, and it's difficult. If you're going to do one, get advice from someone who's done one and ask them, just to take you through the ropes. So what happens when you do it? So you get this page, and it says, "I have read the terms and conditions," and you just click. You don't read them. You just click yes. I think in there it's like, if you don't fulfill, you've got to pay everyone their money back, but whatever. You worry about that when it gets to the problem. Anyway, so you click launch, and then it says, yeah, your project has been launched. Good luck. And in the background, you can see we're at £0 and 29 days to go. And then at the very end, so here's 1 second to go. So this is when it was finished. And we had surpassed all our expectations. And doing a Kickstarter, it's a full. I thought, I'll launch the Kickstarter and then I'll do all the coding while it's running. And but no, when the Kickstarter launches, you've got got a month of answering emails of people who are asking you questions, who are like, "Wow, this is cool," or this is, you know, you beat me to it, and I hate you, and no, I got one that was very similar to that, because, anyway, but before we launched, we were really worried that, you know, because it was a time when everyone was doing these Arduino projects, and there was Espruino, the JavaScript version, and we were really worried that we were going to get beaten to it, because MicroPython seems like such a good idea. I'm like, you know, why hasn't someone done this? And I was really worried, and luckily we made it in time. And then we had to fulfill, so you don't get £100,000 to spend on a car, you get £100,000 to do all this stuff. And one of those things was to make boards, this little board that I was demonstrating before. So we called the Pi board. So we decided not to go in China and try and get it cheaply done, but to do it locally in the UK, which was just down the road in Luton, about an hour's drive from Cambridge. And it was really good. I mean, we got approached by many different manufacturers from UK and abroad, and Geltec wooed us with their free lunch and yummy food. So they said, you know, come over and have a look at our facility, and we did, and we walked through, and there's a picture in top right corner there. It's really nice to be inside a factory where they make stuff, because it's like, normally you're coding away, but if you go into a factory and you see things coming out of a production line, it's very cool. They had a nice facility. Normally Geltec do really high-end stuff, low volume. Like they built parts of the LHC, this collider that I was sort of part of when I was a physicist. And they'd never done such a large volume production before, making 3,000 boards. They're like, 3,000, that's a massive number. And so, but they're small, you know, so we wanted to get small, low cost per unit, but many of them. And because they were so keen to sort of help us and get into this space of more consumer grade rather than high-tech grade products, they gave us a really good price on assembly, which matched the other prices we had, and so we wanted to go with them. And yeah, it was really good. I mean, there's always a few little bumps along the way with the manufacturer, because, you know, when you make 3,000 of something, the little errors, they always come in. You know, even if there's a 0.1% error of something happening, if you buy 6,000 switches, 0.1% of 6,000 is a few. So a few switches break, for example. So when you're dealing with such large numbers, there's always things that go wrong. But Geltec were really, really helpful all along the way. The first batch of, so you're making a panel, the bottom left corner, it doesn't show the full panel, but there's 24 boards in a panel. And the first one that came off the line, I was there to see it come out of the oven and was going to test it. So we tested all 24, and I think 16 were broken. And that's not very good yield. So Geltec were helpful. We sat there, we had an oscilloscope, and working out what was wrong. And in the end, it turned out that the capacitors for the load capacitors for the crystal were not the right size, because the data sheet was wrong, and so we changed them. We tried all different sizes. So they were at 27 picofarad, and we tried everything from 27 down to 10, and then picked the middle one that worked, and then made the rest of the boards with that revised capacitor value. And luckily, they all worked. After they come out of the factory, then you get all these things to ship to people. So there's these boxes. We put them in little black boxes, and on the right, there's the boards with header pins soldered in, and you get boxes of parts, and you've got to put them all together into kits. So what you do is you go to your local university and hire all these PhDs, postdocs. Well, I mean, because I was still at the university then, and I had lots of good friends. So I think in this room there's like 4 PhDs in theoretical physics, or at least in something, and masters of business and everything. I mean, they're way overqualified, but programming and packing boxes, and this is a little house in Cambridge, and yeah. Anyway, so this is if you've done a Kickstarter, you know what it's like, and if you've seen photos from other Kickstarters, you've probably seen something similar to this. This is what it's like, and you pack stuff into boxes, into envelopes, and into boxes, and actually you do things sort of on the. You don't have time to plan, so we're like, okay, how do we ship 2,000 items around the world? And let's put stamps on them. And then you go to the post office and you're like, well, we need £500 worth of stamps, like $1,000 worth of stamps, please. And they're like, okay. And they actually had it at the time, and they counted out 500 pounds worth of stamps. So we took them home and we put them on all the things. And I went back the next day and I was like, I need another 500 pounds worth of stamps, please. And, but they said, oh, sorry, someone came in yesterday and bought all of our stamps. So we don't have any left. And I said, well, what can we do? And they said, well, you can buy them online. And so we ordered more stamps online. But the right solution was actually to do this like printed postage and you can print your own stamps. But we eventually got there, but not at the start. Here is more bags. So these are like postage bags full of stuff. This is a typical Kickstarter picture. Anyway, but it was a lot of fun doing a Kickstarter and also a lot of stress. But you know, you learn stuff and it didn't kill us, so it made us stronger. I hope. Well. So anyway, back to some technical stuff. If you ask me, you know, why did you write this piece of code this way? And most likely the answer is so that it reduces RAM usage, because as I said before, RAM usage is the biggest problem on a microcontroller. So there's just a list here of sort of some of the tricks that I've used to reduce RAM usage. And yeah, I don't need to go through them all in technical detail really, but I think there's one. Oh, hang on, sorry. Let me go back. There's one trick we use so that you don't have to allocate memory for numbers all the time. We use this thing called pointer tagging or pointer stuffing, which was borrowed from Lisp, or maybe even someone invented it before Lisp. But you have a 32-bit pointer which points to your object normally. But actually, you can use the lower bits because they're always 0. So if the lowest bit is actually a 1, then the rest of the bits encode the integer. And if the lower bits are 0, then the rest of the bits are actually a pointer to the object. So you're reusing the address space of all your pointers in order to fit more stuff in the pointers. So integers that fit in 31 bits don't take up any memory on the heap. They're sort of in place. Stored in place. There's no reference counting in MicroPython, only garbage collection. That reduces the memory usage of objects because you don't need this extra information to do reference counting. It also means the code is smaller because you don't have to increment and decrement references all the time. But I mean, yeah, it also means you have other problems though with having no reference counting. This is sort of a diagram of how the internals work. Don't worry if you can't really read it, but if you start at the red box, that's where the scripts start. So you either have a REPL prompt, like you're typing in code like I was before, or you have a script, or maybe you have a string that you're compiling using eval or something like that. And that comes into the lexical analyzer, which splits the string into a stream of tokens, like 1 and plus and 2 and if and colon. And then that stream of tokens goes into the parser, which turns that into a tree, which has structure depending on what the language is. So it'll be plus, 1, 2 in the tree, which means the plus is applying to these two objects. And then that parse tree goes through the compiler, which turns it into bytecode. So it's like, to do a plus 1 and 2, I've got to load 1 onto the stack, then load 2 onto the stack, and then do a plus operation. So it translates that into bytecode. And then that bytecode gets executed by the virtual machine, the orange box sort of in the middle. And the virtual machine relies on a lot of runtime code, which is code to like sort lists or search dictionaries or split strings. So all the things that you can do with strings, like searching or string.ends with, that's implemented by some runtime functions, which are just written in C. So yeah, that's the basic way MicroPython is structured. Normal Python is also structured in a very similar way. Okay, this slide is a bit more detail about how the pointer stuffing works. So the x's represent, and the 1 represents your object pointer. And if it's a 1 in the lowest bit, then the x's are actually the integer. And in all of the code that runs, it checks if there's ever an overflow. So if I've got the biggest number I can store in 31 bits and I add 1 to that, I don't want to overflow like I do in C. I've actually got to now do something else. So it actually makes a big num, which is an arbitrarily sized number. That's stored on the heap, and that can use as much memory as it likes. But usually you don't go up to such large numbers. But they're there, as I showed you before, if you need them. So there's this transparent transition between numbers that fit in a word, a machine word, and numbers that don't. And then we also optimize the way strings are stored by that bit pattern you see there. And then some of the work I did on the ESA project, which I'll talk about later, we introduced the 64-bit NAND boxing object model, which is optional if you want to use that. So if you know what that is, then yeah, you understand. It just means that the numbers are twice as big and you can actually fit floating point numbers in place. You don't have to store them on the heap either. You can ask me later if you want to know more details. So there's a few extra things I added because I wanted to make it the ability to run code fast if you needed to on a microcontroller. So normally code, I said, turns into bytecode. Scripts that you've written, like this add function, is compiling into these 4 opcodes, which each take up 1 byte. The left column is the offset, the middle column is the opcode value, and the right column is just a human description of that opcode. So to add x and y, you load x, you load y, and then you add, and then you return. So it's quite straightforward. And this is the default way of compiling, but you can force this compilation mode by adding this decorator at micropython.bytecode at the start of the function. Okay, so that becomes important for the next slide, because if you change at micropython.bytecode to at micropython.native, now I don't expect you to read or understand any of that text there, but what happens then is that instead of emitting bytecode, it emits machine code. So what's happening is so the virtual machine can execute simple bytecodes like load and add, but all the virtual machine is really doing when it executes one of those is executing some machine instructions that will do that operation. So what we do here is instead of writing out the bytecode, we write out the machine instructions that the virtual machine would have executed for that bytecode anyway. And so those bytecodes from the previous page, I'll just go back, this load fast stuff, binary op add return value, they're all expanded by the compiler into these machine instructions. So this is machine code for an ARM chip running in non-thumb mode if you're interested. A lot of it is set up to decode the keyword arguments if you've passed them in. Actually, the real code is sort of at the bottom. Yeah. And if you have code like this, it uses more memory, but it runs about twice as fast because you don't have the overhead of the virtual machine. So that's kind of nice. But one of the big things I wanted to do, so if you write for microcontrollers in C, a lot of the time you have a little bits of inline assembler because you want to maybe turn interrupts off and write to this special register and then turn interrupts back on again, just because that's what you have to do to do some special feature with the microcontroller. And I didn't want to take that away with MicroPython. I still wanted you to have this ability to really go to the low level of the machine if you needed to. So if you decorate your function with at micropython.awesomeness, that means that the next function is written in machine code, assembly, and is converted directly line by line to the corresponding machine code. So in this case, the function SumBytes will add an array of memory so you pass it an array of memory and it adds the bytes in that memory and returns that as a number. And this is the code to do that written in ARM thumb code. So you move, branch, label, load, byte, add, subtract, label, compare, branch if greater than, and move. So the last instruction there, that move R0, R2, that's sort of like return, because R0 is the return register. So an R2 was the accumulated value. Anyway, this function does work, but the main thing is you can now call it like a normal Python function. So SumBytes is just a Python function called SumBytes, and it takes 2 arguments. So down the bottom there I have an example of how it's called. So I'm passing it, the first argument is the number of bytes to add, and the second argument is an object with hopefully, it could be a string or an array or anything that has bytes in it, essentially. And then it will return you a Python object, like an integer, representing the addition of those bytes. So this is really useful when you want to do some low-level stuff really fast. And then you don't have to really give up anything by using Python. Because Python is slower running on a microcontroller than C, and that's just unavoidable. So this gives you some advantage back if you need it. I'll just briefly say the coding style in MicroPython is not traditional software engineering. I'm not a software engineer, I'm a physicist, and physicists write code really bad. Well, maybe not bad, but not really well. But with MicroPython, it wasn't about making it a good code base, it was about making it actually work. And from the beginning, I didn't know if it would work, so it was like, whatever, I'm going to use gotos everywhere. I'm going to optimize first and make it work later. So a lot of the decisions that were made based on analysis as well, like analyze a million lines of Python library and see what the most common bytecodes were or whatever, just to see how to encode things better, for example. And we have this dashboard which tracks the size of the code and the performance of the code. So the red jagged line is the Pi stones for MicroPython. That went up after doing some optimizations. And the other lines are the size of the code. We just try and make sure it doesn't grow too much. It's on GitHub, and I think GitHub is an amazing community of coders, and people can just come to a project, submit a bug report, submit a pull request, or just contribute to the discussion. And having it on GitHub has really helped the project grow, because people can run it on all different machines, submit bug reports for those machines, and just contribute in general. And it's been really great. We have quite a lot of stars and lots of forks and over 100 contributors. I couldn't have done it without the help of the community. And I think having open source and being on something like GitHub helps a lot with that. Just for your interest, here I scraped GitHub a little bit to find out the stars of all the top projects, because I was interested to see sort of what, when you have 3,000 stars, what does it actually mean? It could mean nothing, or it could mean you're the best, So here, there's a lot of JavaScript projects on GitHub, so I filtered only the C and C++ projects. And this is the top, the top list from 1, and then I skipped a few and down to 113. This was done last year, and it takes a bit of time to do the scraping, so I didn't redo it for this year. But the rankings pretty much haven't changed, just everyone's stars have gone up by a lot. But you can see MicroPython is almost position 100, so we're doing okay. At the top is Linux, which I guess you'd expect. But yeah, Raspberry Pi Linux is just up there at 100. So yeah, MicroPython can run on really small hardware like this Pi board that I showed you, and there are its specs. There's another platform, the YPi, which has Wi-Fi built in, and then this ESP chip, which I talked about yesterday in a talk, only has 96 kilobytes of RAM, although the heap is only 32 kilobytes on that one, or maybe even less, about 24. And yeah, it's really constrained, but MicroPython still works. MicroPython also runs on your computer if you want to use it as a lightweight version of Python, maybe on an open WRT like system that you have, or other really embedded constrained system. It also runs on this thing called the microbit, which is a BBC project that we were involved in along with the Python Software Foundation. I won't really talk too much about it. Ask me later if you'd like. It's a very constrained device. 256K of flash and 16 kilobytes of RAM is really small. But it has a lot of LEDs, and 1 million of them were made and given away, or about 700,000 were given away for free to all of the year 7s in the UK so they can learn teaching. Because the curriculum in the UK has changed from IT, like Excel and Word, to actual computing, like programming. And kids are now on the curriculum, they're required to learn at least 2 languages, one of which must be text-based, like Python, for example. And because a lot of teachers already know Python anyway, and kids have been learning it, we think using the microbit with MicroPython, it's almost a seamless transition. So they know Python, and now they can actually make some cool stuff with this microbit. So I'll just do a little demo, because there's a lot of hard work's gone into developing the microbit here. Let's cross our fingers that it works. Okay, so this works just like the PyBoard demo I showed you before. You just log in with a serial console, and you type A, and it gives you A back. Okay. But it can do 1 + 2. And I think it can even do like, you know, okay, it's a bit slower. It's running only at 16 megahertz. The other one was at about 160 megahertz. So, but the cool thing with the microbit is we have implemented a speech module, and you can say whatever you like. So let's see, Australia. So this, a lot of hard work has been put into this, mostly by Mark Shannon, who maybe some of you know, who's a core Python developer, and Nicholas Tollervey, who you might also know. So yeah, the three of us have worked quite a lot to get this going, and Nicholas really pushed to get this speech module because he thought it would be really cool for kids to have this in their classroom. They could, well, you can imagine what the kids are going to say in a classroom. I won't write it here because that's probably not allowed by the code of conduct. But so, if you want to hear this again, but just to show, I mean, whatever I type, it will talk. But I mean, it's not pre-canned code. It's got an American accent, I think. Anyway, so, but this is just normal. This is Python with a few extra cool things like the microbit. You have a display, and I can show like an image, a heart, or happy. But yeah, I won't pick it up because it might just destroy the sound. But it has a nice little display, and you can do lots of things with it. It's a fun device, and we think that the kids will really like using it. They've been starting to use it, and we have a lot of good feedback. And there have been other countries around the world that have been interested in implementing this as well. But anyway, I have to get to this last bit because this is an important part of the talk about the European Space Agency project that we were doing. So I got an email. The Kickstarter finished, and it had been a few months into the work. And I got an email, and it said it was from someone at the European Space Agency, the S-Tech part, which is in the Netherlands, their technology group. And they said, "Do you think MicroPython can run on a satellite?" And I said, yes. I didn't even think about it. I'm just like, yes, I think it can. And then they said, well, that sounds good. And then they asked a few more technical questions. You know, we've got a constrained system. Space computers were built in a long time ago, and they haven't been changed because they've got to be hardened to radiation and proven and all this stuff, and it costs hundreds of thousands of euros to actually prove them. So once you've done it, you don't want to do it again every year. So space computers run at like 80 megahertz and have 16 megabytes of RAM. So they're very constrained and usually written in C. And what you have to do, so your satellite's up there and you're like, okay, I have to change the program. So you turn the satellite off, and then you upload your new C code that you've tested on the ground, and you turn your satellite back on again, it boots up and it's running your code. And this is a pretty painful iterative process, which is why, well, there's lots of infrastructure on the ground to make sure it's as efficient as possible, but it's still not great. So the idea they had was, well, we want to have a scripting or a high-level scripting language running on the satellite that we can easily upload scripts to without turning the satellite off or without interrupting any of the other services. So MicroPython won't be controlling the boosters, for example. That will be, which... maybe in the, I don't know. That'll still be written in C or Ada, but so MicroPython's acting like the application level language. So you've got operating system, you've got all the drivers, and you've got the kernel, and you've got the Wi-Fi stack, and then on top of that you've got your Python code, which does all of the the actual user-facing stuff. So the same idea with the satellite is you have a scripting language which does the top-level stuff that's not super critical because the boosters are still controlled at the C, and they've got lots of testing or lots of checks to make sure things don't go wrong. But you can easily change the script to say, okay, we've got a solar panel's broken, why? Okay, let's upload a debugging script which can check all the currents and the heaters and everything and check what's wrong, and then download all that data. Then once we've worked it out, we can upload another script to fix it, and then upload another script to run with the disabled solar panel, for example. So it's really easy to change things on the fly. You won't have a REPL in space because of a few problems. One, the satellite moves, and you lose communication with it. And two, because of the time delay. I mean, to the sun is 8 minutes, to the moon is, 30 seconds or 8 then? 30 seconds maybe. So you can't have a REPL really in space. But you can, the idea is to be able to compile scripts on Earth, verify they're working, and upload them. So we did a 10-month contract with the European Space Agency, and there was a lot of red tape, which is annoying, but once you get through that, there's a lot of really fun coding, and there were lots of good things that came out of it, like NAND boxing support and separation of compiler and interpreter. And all these things went, well, most of them went back into normal MicroPython under the MIT license. ESA, the European Space Agency, were very, very happy to do that, because the way ESA works is it's an agency which gathers money from all the European countries and then gives it back to companies within the European Union to do work. So ESA themselves don't actually do that much, or S-Tech. So they just write contracts, hand them out to those who bid for them, and then check the results. So they're really happy to have companies like ours join the team and take a contract and do some work and build the economy that way, and then give all our work back for free to the community. So yeah, ESA are not this closed company that you might think, and all the stuff's proprietary knowledge. A lot of it is freely available if you're in the EU. So this was an amazing opportunity. I mean, I think for me it was probably the biggest thing that came out of this project so far, is that I got to work. I mean, I always wanted to work for ESA or NASA, say, but having a company contracting is probably even better. So it was really cool, really cool. You can ask me more about it, and I'm happy to talk all about what we did. And then actually we went and did another Kickstarter for this ESP8266 Wi-Fi chip, which I talked about yesterday. So even after doing one Kickstarter, I'm like, I'll never do another one. And then I did another one, but we got a great response. It was software only. We didn't give any hardware away, but we still got almost 50,000 equivalent Australian dollars, and a massive, massive support, people who just wanted to see the project succeed further. There's been a lot of challenges. There's a list here, but the one that I'll talk just briefly about is, I think the hardest thing is managing a community and expectations. So, it's free software, but people still complain and ask questions, file bug reports, and are like, why doesn't this work? And I know I like to try and fix things, but at some point you run out of time to fix everybody's problems. But I mean, managing a community is hard, really hard, and also it's hard to be a manager of a project and also do all technical coding, a lot of technical coding as well, which I still like to do. And monetizing a project with the company that we have, selling hardware, I think is something we're doing, and also contracts with the European Space Agency and some other people. I don't think you can have an open source software project without some kind of monetization, and we're really lucky that we have some streams like hardware to do that. So I think my time is pretty much up now. This is my concluding slide, which has just a list of things I talked about. So, I mean, MicroPython is seen used in lots of places, like, for example, in coffee machines. There's a university course in France built around MicroPython to teach embedded systems. Labs using it to automate, heating and cooling of their blood samples, for example, in some biotech labs. And there are lots and lots of hackers around the world just using it and playing with it and contributing back. So there are many applications, and I think it's still growing. The Internet of Things is a massive area which is only just starting off. And if Python can run the normal internet, maybe MicroPython can run the Internet of Things, the micro-internet, or at least be part of that in some way. So you also saw, in space, we actually have a couple more contracts coming up with the European Space Agency. So they really like the first bit of work, really happy with it, and think that it may be that it can actually go into space. So the first project we did was a proof of concept, and we'll be doing at least another one, maybe 2 or 3, to further integrate it into their system so that it can maybe one day go into space as this application layer language. There's other things. There's multi-threading support that's recently gone in and not yet available on the PyBoard, but should be soon. Hopefully the microbit we can optimize that to get a bit more memory. And yeah, we're also looking to develop some more hardware. We've got lots of ideas, but sadly not as much time as ideas. Anyway, so trying to focus on things like housing for the board and there's lots of new chips coming out in the market, and getting them to run MicroPython would be really cool. So that's what we're looking at the moment. And so yeah, I mean, I work full time for my company doing MicroPython stuff, and it's a lot of fun. I get a lot of freedom, like I did in physics. And here are some websites you can visit if you'd like to learn some more. The forum has a lot of discussion. On GitHub is all the code freely available if you want to look through it. And this is a picture of our board, which are for sale on our web shop. But thanks for listening.